Have you ever wondered, what if a computer could explore every single possibility, all at the same time? I know it sounds like something straight out of sci-fi, right? But believe it or not, that's the very real promise of quantum computing. So over the next few minutes, we're going to break down the three, frankly, kind of bizarre quantum principles that make this whole thing work. We'll start with the massive leap from our regular computers, then we'll dive right into the three big pillars: superposition, entanglement, and interference. And then we'll wrap up with what this all means for, our future. Ready? Let's get into it. Okay, so to really get why quantum computing is such a huge deal, you gotta look at what's holding back the computers we use every day. Just think about solving a really complex maze. A normal, classical computer. It tries one path, oops, dead end. It backtracks, tries another one. It'll get there eventually, but it's slow. A quantum computer, on the other hand, could explore every single path, all at once. That is the mind-blowing difference we're talking about here. You know the phone or laptop you're watching this on right now? It runs on something called bits. And a bit is super simple. It's like a light switch. It's either off, which is a 0, or it's on, a 1. That's it. But quantum computers, they use something totally different, called a qubit. And here's where things get weird. Thanks to the wild rules of quantum mechanics, a qubit can be a 0 and a 1 at the exact same time. So how on earth is that possible? Well, that question brings us right to our very first core quantum principle: superposition. This is the magic that lets a qubit exist in that strange, in-between state. So, superposition basically means a qubit can be in a blend, a mix of both 0 and 1. It's not one or the other. It's this whole spectrum of possibilities happening all at once. And this idea, it's the secret sauce. It's what gives a quantum computer that incredible power to work in parallel, to explore millions of scenarios in an instant, because it's holding all the possible inputs at the very same time. You know, a really great way to wrap your head around this is to think of a spinning coin, right? While it's flipping through the air before it lands, is it heads or is it tails? I mean, in a way, it's kind of both, isn't it? That coin only picks a side, heads or tails, the moment it lands and we look at it. The moment we measure it. A qubit in superposition is exactly like that spinning coin. It exists in this sphere of possibilities, holding all of its potential answers at once, and it stays that way until we make a measurement, which forces it to collapse into a definite 0 or a definite 1. And this is where things get absolutely insane. This power grows exponentially. So 2 qubits can hold 4 states at once. 3 qubits can hold 8. But get ready for this. With just 300 qubits, you could represent more possible combinations than there are atoms in the entire known universe. Just let that sink in. That's an explosive, almost unimaginable level of power that classical computers can't even dream of. And that's why this is such a game changer. Okay, so superposition gives us this ridiculously huge space to play in. But having all those possibilities is only half the battle, right? How do you make them all work together in a useful way? Well, that brings us to our second pillar: entanglement. Entanglement is this wild phenomenon where 2 or more qubits become linked, inseparably tied together. Their fates are intertwined, and from that moment on, they act like a single system, even if you could put them on opposite sides of the galaxy. This connection was so bizarre, so counterintuitive, that Albert Einstein himself famously called it spooky action at a distance. He just couldn't get his head around it. But here's the thing. It's been proven to be 100% real. And this spooky link is a critical resource for quantum computing. It creates connections between qubits that are just impossible with normal classical bits. So, here's the crucial part. If you have 2 entangled qubits, the instant you measure one and find out it's a 0, with absolute certainty that its partner is also a 0, instantly, no matter how far away it is. This creates this deeply connected system that lets us perform calculations that are so complex, they're just off the table for any regular computer. All right, so let's recap. Superposition creates a massive space of possibilities. Entanglement links them all together. But now you've got millions, maybe billions of potential answers all floating around in there. How in the world do you find the one right answer? That's where our third and final pillar comes in: interference. Interference is basically the quantum computer's secret weapon for finding the needle in the haystack. It's a way to manipulate the probabilities of all those states. You can literally crank up the volume on the correct answer while telling all the incorrect answers to, Well, to cancel each other out and disappear. The best way to think about this is to imagine waves in a pond. You know what happens when two wave crests meet, right? They join up, they add together, and they make a bigger wave. But what happens when a crest, a high point, meets a trough, a low point? Well, that's exactly it. When two crests meet and get bigger, that's called constructive interference. But when a crest meets a trough, one up, one down, they just cancel each other out completely. That's destructive interference. And believe it or not, the probabilities inside a quantum computer behave just like those waves. So you can think of a quantum algorithm as a carefully choreographed dance. It's designed to guide all these probability waves so that the wrong answers smash into each other and just vanish through destructive interference. Meanwhile, all the paths leading to the right answer all add up and reinforce each other, getting bigger and bigger. So by the end, it's the one you're almost guaranteed to see when you finally take a measurement. It's pretty darn clever. Okay, let's bring this all home. Superposition, entanglement, interference. These aren't just three separate party tricks. They have to work together perfectly to get the job done. So first, superposition blows the doors wide open, creating that massive workspace to explore everything at once. Then, entanglement steps in to link all those possibilities into one single, interconnected system. And finally, interference acts as the ultimate filter, canceling out all the wrong answers and amplifying the right one until it's the only thing left standing. So why should any of this matter to you? Because this new way of computing could help us solve problems that are right now completely impossible. We're talking about discovering new medicines by simulating molecules from the ground up, or solving mind-bendingly complex problems like optimizing global supply chains. This isn't just about building a faster computer. It's about inventing a whole new tool for discovery, one that could tackle some of humanity's biggest challenges. Now, let's be real for a second. We're still in the very, very early days of all this. We're in what people call the NISQ era. That's noisy intermediate scale quantum. And all that really means is that today's quantum computers are incredibly powerful, but they're also super fragile. They can get thrown off by the tiniest bit of noise, a little change in temperature, a stray vibration. So right now, the biggest challenge for engineers is just making these things more stable. But that leads to a final, pretty powerful thought. We are building machines that operate on the fundamental laws of the universe itself. Sure, they're noisy and imperfect today, but the progress is happening incredibly fast. So the real question isn't if we'll build a stable, full-scale quantum computer, it's when. And what happens to science, to medicine, to our whole world when that noise finally fades?